Let's begin. Blake, let's begin. Okay, so we have looked at two previous formulas up to now. I'm going to give you one last one today, and then you're going to get a chance to do a little handing assignment so that I can see who gets it, who doesn't get it, and then we can go from there kind of thing. So after today, you're going to know what resistance is. Electrical resistance. I'm not talking about the resistance, like the Rebel fighters in Star Wars. And you're going to be able to solve V equals IR problems. So before I begin, I ask you...
I think we already know how to solve them.
No, not those ones. Oh, no, not those ones. No. What do you think electrical resistance is? Like, what does the word to resist mean, I guess? Let's start with that. To go against? To stay away from? Anyone else? What does it mean to resist? Blake, I need you to listen. Not accept? I like this one. What did you say? Was it you?
To go against.
To go against. Right? If you resist, like for example, if I say, Jeff, I want you to go to the office.
No.
Perfect example. Well done. That might have been a little bit too much, but I'll let it go because we were playing it. This is supposed to start up a video. We'll see if it does. Let's continue. So, now that you've seen that, what can you tell me? What is resistance, Blake?
It's the force of one object moving another force that pushes against another.
Okay, well, let's first of all, remember we're talking about electrical resistance.
So, if I want to push, or you want to push me, I push you back.
Okay.
Is this resistance? If you're biking and the wind is going against you?
Yes, that would be a good analogy for resistance. In electrical resistance, what's moving?
You.
Not me. Electrons. Electrons are moving, and what are they bumping into, Andrew? As they move down the wire.
What?
As the electrons move down the wire, what are they bumping into?
Other ones. Other electrons.
What atoms?
Atoms.
Are the atoms moving, Blake? No. They're fixed in place, right? They're like the people standing around the mall doing nothing, causing trouble. Okay, you have this handout, right?
Do that.
No.
Now you do. It's right there. You have the PowerPoint slides. What is the symbol for R, or symbol for resistance, Blake?
R.
R. The symbol for resistance is R. When I say symbol, I mean what is the letter that represents resistance? It's R. It should be on the second slide. Right there. Now, what is the unit for resistance? I heard it. It is an ohm. Ohms. Ohms. And the symbol, like, you know how we use I'll tell you what it is. You know how we use cm for centimeters, or n for newtons, or V for volts, or stuff like that? Okay, so that's the symbol for ohms, and it's the Greek letter omega. It's the Greek letter omega. I think it's their O, actually. Right? I remember when I was a kid, we had a car that was called an Omega, and it had that little symbol there on the steering wheel. And it was named after anyone? That guy, yeah, George Simon. Oddly enough, his last name was Ohm. Where's his picture? Come on, give me the picture. There he is. Okay, so yes, George Simon Ohm. He was a German physicist and mathematician. As a school teacher, Ohm began his research with the new electrochemical cell invented by Italian scientist Alessandro Volta, who I wonder, what do you think we named after him, Blake? Volts, right, the volt. Using equipment of his own creation, Ohm found that there is a direct proportionality between the potential difference, the voltage applied across the conductor, and the resultant electric current. This relationship is known as Ohm's law. Not only did he get a unit named after him, but he got a law named after him.
Ohm's law.
Lucky guy.
Just like Newton's law.
Just like Newton's laws. Newton's got 3 laws, right?
Did he actually?
What?
Yes, 3 laws.
Newton, yeah, 3 laws. Okay, so symbol is R, the unit is the ohm. Okay, so I think you have to fill in some blanks here, right? I think you have to fill in some blanks here. So as the electrons move through a conductor like a wire or something like that, they bump into the fixed particles, the atoms in the conductor. When they bump into the atoms, the electrons slow down and give up their energy as heat and light. This opposition to the flow of electrons is called resistance. I'll pause there for a second. What is Ohm's law then? Well, that's the formula for it, right? The law itself in words is the current in a wire, I, is equal to the voltage divided by the resistance. It's directly proportional to the voltage and inversely proportional to the resistance. The greater the resistance, the more pushback, the more kinks in the hose, the more people in the mall, the greater the resistance, which means less current. Like, you gotta listen to me. The more resistance there is, the less current. The greater the voltage, the greater the amount of energy, the more current there is. Do you guys have to write that down or no? It's there. It's there? Excellent. In formula terms, the current is equal to the voltage over the resistance, or I is equal to V over R, and we measure it in amps is equal to volts over ohms. Those 3 things are sort of all the same. Current is voltage over resistance, I is equal to V over R, amps is equal to volts over ohms. I asked you previously, are there any examples that you can give me, Blake, where we use resistance for good? How do we give off, how does the energy get given off? How does the energy get given off? 2 ways. What are the 2 ways?
Oh, big time.
What are the 2 ways that energy is given off? No. 2 ways.
Heat and energy.
Heat and light. Exactly.
Heat and light, I got it.
Heat and light. Can you feel the heat?
No.
Yeah.
You can, but I can. How come?
But
Is there resistance happening in my projector? Absolutely. Here are some examples. You have them right in front of you. Everyday practical examples of Ohm's law. How many people have a baseboard heater in the bedroom? In the house. Lots of people do, right? Right? You got one of those in your house somewhere? Have you ever looked closely at it? Look. It's basically, it looks like a coat hanger in there.
No, it looks like a rat radiator.
No, but if you look right inside, it looks like a coat hanger in there, right?
It looks like a rat.
All it is you're running electric current through a wire, and because it's meeting resistance, it's giving off the energy in the form of heat, which you want in your bedroom, because it's cold in there. Other examples, electric frying pans, toasters, electric light bulbs. When you run the energy through there, okay, what happens? The light bulb does what? Lights up. Lights up. Exactly. It gives off light and it gives off heat. We're using resistance for good. The heater consumes power producing heat for warmth. Frying pan consumes power for producing heat. Toaster, look inside the toaster. What do you see? Don't stick your finger in there. You see little wires. Basically, you're running electricity through wires and it's giving off heat.
I watched a video of a guy had a toaster on, and he took a knife and he stabbed it inside the toaster, and the toaster just blew up.
Wow. Awesome.
Exploded. Oh, I almost did that. No, like literally, but it exploded.
Okay. No, I want to do this. I want to do this. You wait. I want to do this. No, you wait. No, you wait. Here we go. I bet you write this example down. You have it right there, right? Let's do a solution. What's the formula, by the way? Yes. I equals V over R. Okay. What's our steps for solving the problem? Guys, very soon I'm going to ask you to do problems just like this, and then you're going to say to me, I don't get it. then I'm going to say, but I just showed you how to do it. And you're going to say, oh, I wasn't listening. Here, let's go back and let's maybe you listen, and then you won't have to say it again.
All right.
Let's do that. Let's try that. Okay, a toaster has a resistance of 100 ohms. So I'm going to write R equals 100. R equals 100. Resistance, 100 ohms. If the potential difference in an outlet is 120 volts, that's what you get when you plug in your toaster at home. So V equals 120. And I'm solving for calculate the current. I'm solving for I. That's what I want you to write on the left-hand side. What you know and what you don't know. Write that down, please. See it right there? Right there. Now we write down the formula. Plug in what you know and what you don't know. I, we don't know. V is equal to 120. The resistance is 100. 120 divided by 100. 1.2 what? What do we measure current in? Amps. 1.2 amps. A. The current is 1.2 amps. It's just dividing. It's a calculator. It's 120 divided by 100 on your calculator. I don't expect you to be able to do that in your head. I do expect you to be able to write this stuff down, write the formula, and line it up. Okay? No, I'm not done. But thank you for waiting. Okay? I'm going to get you to do questions just like this in the very near future, Andrew. Okay? Blake, have a seat, please. Okay. Last one, and then it's going to be your turn.
Oh my God.
15 coulombs of charge are moving through a wire in a minute. If a 100 ohm resistor is added to the circuit, what would be the potential difference? You're going to need two different formulas. It's a two-step one, Jeff. Two-step formula.
Why is it 2 steps?
Because it's concrete.
What?
You like that, do you? Oh, good.
Yeah.
Blake up here, not back there. She's fine. I'll let you know if she needs help.
I'm just worried about even.
He's fine too. If he needs help, I'll let you know. He's got his hair to protect. 15 coulombs of charge. What does that tell us, Blake? 15 coulombs of charge. What's the letter for charge?
Q.
Q. Very good. Q is equal to 15. 100 ohms. So R equals 100. And I'm trying to find out potential difference. V. I'm trying to find V. Uh-oh. Okay, so I need two formulas here. I need one with V in it. Should we write out all the formulas that we have? The latest one that we have is I equals V over R. And what are the ones we had before? I equals Q over T, and there's one with E in it.
I equals Q over V.
What's the one with E in it?
Because U.
Yeah.
I equals Q over V.
Thank you. All right. What's the third one with the E in it? Help me out here, because I'm old people. What is it? Q what? Q equals E over T? V. V E over V. Is that the one? Okay. So I'm trying to. I need a formula that has V in the end, and I got to start with Q and R. Uh-oh. Oh, hang on. Oh no, that's right. 15 coulombs of charge. We need to figure out what E is.
It's the wire per minute or whatever. Minute.
Oh! We know something else, don't we? You'll notice here But you'll notice here that I didn't put, I got 15 in numbers, I got 100 in numbers, but here I've got minutes in words. I stuck it in there. So I know one more thing. Oh yeah, I've got T is equal to 60 seconds. Oh, Mr. Bennett, you are sneaky like a fox.
But I caught it.
So sneaky that I fooled myself there. Okay, so what can I get out of, I know what I can do. Out of Q and T, I can find I. Out of Q and T, I can find I. Okay. So. Watch. So that later when you say I don't get it, you won't have to say I don't get it because you'll get it. What's Q? 15. What's T? 60. The I is 0.25 amps. Okay. Can I use that now?
Yeah.
To solve for V. Which one has V and I in it? Oh, you know what I need to do? I need to do this. Which one has V and I in it? The new one. Blake, are you jotting this down?
I got it down.
The V is what I'm solving for? Oh, now. What I need to do, I need to give you the other versions of the formula, don't I?
Yeah. No.
I didn't do that. Let's jump into the Mr. Freeze and Time machine and go backwards. Can you go back to that slide for me? Yeah. Let's go back to this slide here where it says I equals V over R. So what's V going to equal? I times R. Come on, you. Draw. It won't do it. I'll do it up here. It won't do it. Guys, seriously, if you don't watch, how are you going to get? How'd you do that? It was resisting my writing.
What a voltage. What?
Did you get a charge out of it? No? We want V is equal to I times R. And R is going to equal V over I. You should probably write down those extra ones, right? Right, Ethan? Those are the new versions of them.
Oh.
Alrighty, now we can solve it. So, I'm guessing no, Dawson. So I'm solving for which one here now? V. V equals, what did I just tell you? I think it's I times R, right?
Yeah.
So I 0.25, resistance 100. Being the smart guy that I am, I can do that in my head. 25 volts. Don't stick your tongue on a 25 volt battery. You don't want to do that.
Why? On a what?
25 volt battery.
Will you die?
Stop your heart.
Yeah, it would.
Would it actually?
Yeah, I like it. 12 volt batteries are dangerous.
What about a AA battery?
That one you can stick your tongue on. Go ahead.
Battery. I put on my battery.
Don't eat it though.
Stupid.
Even those flat batteries fly.